I'd like to introduce Sam. Sam is working at WellTyped on GHC. He's a fairly new contributor to GHC. You got started in 2021, I believe. So, but nonetheless, he's already done a lot of very useful things. And he writes in his bio that he attributes all of his success to the community, but I doubt that a little bit. He's currently working on a project to typeset Japanese shakuhachi sheet music in Haskell. So that's pretty cool. So with that, I'd like to turn the presentation over to Sam.
I'd like to start off explaining what we're going to do. In the first half, I'm going to give you an overview of the Renamer and like all the types you're going to need to know just to give you enough background. And then in the second half, then we're going to try to be fixing a bug, but then it's going to be more interactive because I'll show you how to start navigating around the code base, because I think that's the big thing with GHC is you never go into it understanding everything up front. There's always things you don't know. So what's important is figuring out how do you figure out how the various subsystems work? How do you figure out what parts of the code you need to change and things like that? But for the first half, it's going to be a bit more abstract. So what does the Renamer do? So Ryan was alluding to this. The main thing it does is it gives unique identifiers to everything. So I'll show you what data type it uses to do that, but it's so you know exactly whenever you see an occurrence of something, you have a unique reference to it that you can use to figure out what if I say X, which X specifically do I mean? Do I mean this X or this X, etc.? And then there's another thing it does, which is usage and dependency analysis. So that's for things like figuring out if there's dead code, if there's you've imported something but you're not using it, or you're importing something but there's a deprecation warning attached to it or something like that. And this kind of same logic is used to perform dependency analysis on the code. So you're going to figure out if you define loads of things, when you define something in a Haskell module, you can define things in any order. You can refer to something that's at the end of the file at the beginning. But GHC needs to figure out in what order to type check things, because some things need to be type checked in one go, because they could be mutually recursive. So there's a kind of dependency analysis step that is carried out by the Renamer that determines then in what order things are type checked. So how do we refer to names in GHC? There's loads of different data types. So I'm going to be starting off by kind of going over them, and it can be a bit overwhelming. We've got awk name, reader name, global reader element, var, tyvar, id. So these are all kind of ways we have of dealing with identifiers or variables throughout the compiler when we know more or less information about things. So the most basic one is awk name. This is when you have the least amount of information about something. What you have is just, so we use the fast string data type, but you could just think of that as a string. And then it's put in a particular namespace. And so the namespaces are defined here. So you can have variables, you can have record fields, you can have data types, you can have type variables, and you can have type constructors. So like int or bool, they're all considered to be type constructors. And yeah, as the name says, it also counts for things like classes. So that's kind of the first thing you do when you're parsing something. You're going to figure out what namespace something is in. So for instance, if you're in the middle of renaming a type signature and you're renaming the type and you see a variable, well, it's going to be put into this TV namespace, TV name namespace for type variable. And then there's this type here at the bottom, awkenv, which is how we look up when we've got we'll see later on when we build these environments, but this is how we end up looking up into these things. The way we look up, we first look up the actual textual name of the thing, but then it might exist in multiple namespaces. And there's a lot of disambiguation that can happen. So, for instance, you could have a type where the name of the type and the constructor are the same. So, what's also a good example of that? I think sum, the sum new type is called sum, and then the constructor is also called sum. So then you might need to disambiguate. So if I see sum somewhere, I was like, well, which one do I mean? Do I mean the data constructor or do I mean the type constructor? And that would be these two different, so this would be either in this namespace or in this namespace. So that's how you end up looking up with this information. Okay, then the task of the rename is basically to start off with those and give unique identifiers to everything. So what's really important here is what is a name? It's an awk name, which is what we saw before, but we give it a unique, this is just like an integer, saying like, okay, this is that name, but this unique identifier is like 17. And then there's a few other pieces of information we have attached to name. So we have like where was it defined, like what line and column in which module. And then we have what kind of name is it. And this, you generally don't have to think so much about it. I don't think I even know what the difference is between internal and system. But yeah, so there's a few special names which use this wired-in syntax, which means things that are baked into the compiler. So, for instance, lists. The compiler knows exactly the definition of what a list is, and it's like hard-coded into the compiler in a certain way. So it uses those. But generally speaking, and the information you have is you have the full type information. This is typing, which I'll come back to. But the main thing really is name is what the renamer is going to create, and it does that by finding out exactly what each occurrence refers to, and once it's figured that out, it gives unique identifiers to everything and says like, okay, this was x17, this was x37. And then when you're like looking at core, by default, you're going to get these unique printed out, attached to everything that tells you exactly what variables you're referring to. Okay, then we've got this reader name data type, which is kind of what is when you don't, it's like the most general data type when you don't really know what something is. So, because you're going to have a mix of maybe you've imported a module which have been fully type checked and you know everything about. So you might be referring to some of those identifiers exactly by their unique. So this, for instance, if you're doing template Haskell, that's what you do a lot of time, is you refer to a variable from an imported module, but you say exactly like, it's this variable with this unique. So it would correspond to this constructive, this reader name data type. And then otherwise, it handles qualified and unqualified names that haven't been fully disambiguated yet. So this is kind of what you get as the input to the renamer. It's like you don't know. It's like a data type where you have yet to figure it out. So maybe it's just a name that you haven't disambiguated yet, so it would be in one of these. So this is what the parser would be producing a lot of the time. If it parses a Haskell file, it's going to produce an unqualified or qualified awk name. But maybe you got there's some template Haskell, for instance, or some plugins have run, and then there's some identifiers that you will know exactly, I refer to that. So there's two ways of doing that. There's this exact where you refer exactly by the name, and then there's this orig, which is mainly just used internally when you want to say, I'm referring to like the map function in Prelude. And you say like specifically like, this is the module, this is Prelude module, which is different from the qualified ways. Just like this, you can think of basically being a string. So it doesn't tell you exactly what the module is, you still have to resolve it. Whereas here, I'm saying exactly like, I know what module it is, it's here, and then resolve with the rest of the name. So, let's see. Right, and then we've got this data type for variables, which is what we use afterwards in the type checker and when we're doing in core and when we're running the simplifier. So the way it's set up, I'm not sure I have a particularly good justification for why it's set up like this, but we've got type variables and term level variables that are put into the same data type, but they're just different constructors. And a type variable is basically this unique identifier and then its type, or the kind of the type variable. These are type variables that we create in the process of type checking, but at the end there shouldn't be any left. So Simon is going to be talking about those in his talk on the type checker. But you can imagine that you should never see these once you get into core. You should just see normal type variables. Or then this is for term level variables. You got identifiers. And And then I'm sure Sebastian is going to tell you all about all the different pieces of information we have attached to identifiers in his next talk. But so you can have, for instance, what is it? So you got, I think id details is more like a fixed thing you know about a variable when you create it. So for instance, most things are going to be just vanilla, but then maybe they're primops and they're implemented in a different way and they're handled by the compiler in a different way. There's got record selectors, there's loads. I mean, you can look up at the data types yourself and see it has comments about like what the various things are. And then id info is more things that are relevant later on for the simplifier, like does it have an inline pragma and things like that. What is unfolding and stuff like that. Okay. And then, so, any questions so far?
I had a question regarding the previous slide. So if I understood correctly, I think you mentioned something like this: TC tyvar constructors should not be present down the compilation pipeline.
No.
So would it be possible to also use the trees that grow infrastructure with this var data type? So
I think it would be possible. It's in the past, the core data type, we've been reluctant to change and to make it use trees that grow. So this is the core data type that Ryan showed earlier, where you have the various constructors of the core syntax. And it would be possible to change that, but I think, I'll have to look at the source code for when this was decided to use this kind of representation. It's probably like at least 30 years ago. But I think it would be good to split off some of these things. It's just there's a lot of trade-offs that tend to happen. It's like you have to make sure you don't regress performance by doing that and things like that. So I think there's several tickets about exactly this topics like this already on the issue tracker with people suggesting various designs.
So I also guess there's a lack of motivation to apply trees that grow to core because there is, what is the concrete use? I mean, we can live quite well with just ignoring TC tyvar after type checking. And there is an intellectual overhead to doing a trees that grows transformation to it. Whereas the concrete benefit for the source syntax tree is that it's user extensible. If we were to maybe expose core at some point and we were to expose the innards of our var data type, maybe then there would be more concrete motivation to apply trees that grow to the data type. But, at the moment there isn't much. That said, one level lower, at STG level, we actually do apply some selective, trees that grow-ish kind of transformation because we want to have in different passes, different annotations in the syntax tree. So, maybe in the future there might be enough motivation to apply trees that grow, but at the moment I at least don't see as much.
I think Sebastian makes a good point that if we have a way for users to just write core, then that would be a good motivation for starting to clean up these things, because now they don't just exist for the internals of the compiler.
To add to that, I think users can already write core if they're using GHC plugins. Then they encounter the core data types, and they could, in theory, use the trees that grow to add things to that.
Right. I have written core in plugins and regretted every time I have done that. Most of the time, the solution is define as much as possible in Haskell, define everything that can be defined in source Haskell, and that's going to give you an identifier, and then you just refer to that in the plugin. And then there's there might be one tiny step of one thing you can't do in core source Haskell. So then you just write one line of core to just do that. Because if you try to write core by hand, it just gets really... I mean, the problem is there isn't really a type checker for core. There's core lint, which when Ryan was explaining that the benefit of core is that it's typed, It is, but the way that we check the types is we just run this thing that's called core lint, but it's really a type checker for lint. But it's just like some ad hoc pass afterwards that essentially just kind of panics if there's any problems. So it can be quite difficult to like write valid core in a plugin once you start like having to deal with anything complicated. I mean, definitely if you have to do something like write a GADT pattern match in core, that's just horrible. Like you have to deal with so many things that I mean, the point of the compiler, right, is that we take the source Haskell and then we compile it into core, and the type checker is quite complicated because there's quite a lot of filling in that it does. So when you have to fill in everything by hand writing core, it kind of can easily get out of hand and it's hard to get right. Next, I'm going to talk about what information we need, the renamer deals with. So I think a good place to start is tithing. So this is what the type checker knows about an identifier, about some name, something. Like if you write foo somewhere, maybe lowercase or uppercase, what can it be? So for the type checker, it can be these things. So it can be like a term level, like variable or function, and then you have, and it would use this information here. It could be a constructor. So this can mean either data constructor or pattern synonym. It could be a type constructor, or it could be what's called a coercion axiom, which basically means a type family, or like information about how a type family reduces, or how a new type, like a coercion that unwraps the new type. But you don't really have to think about this most of the time. So this is what the type checker needs to know about things. So when you look up something, usually the information you end up getting is you get a tie thing. So it's like you'd know it's one of these things. And if you know ahead of time what kind of thing you're looking up, you're like, I'm definitely looking up a data constructor. Well, you're going to look up and then you're going to just assume you land in here, and that's going to have information about the data constructor. Right, so the reason I'm telling you this is we have a kind of equivalent to this in the renamer. And the renamer generally doesn't need to know as much about things as a type checker, and can't because we haven't type checked yet, so we don't have full information about things in the current module. But we still need to know some information when, for instance, we're renaming like a record update. When we're renaming things, we need to know things like what data constructors have which fields and things like that. So this is the data type we have currently. And most things are vanilla, like functions and stuff like that, just like no particular information. And then the information we have otherwise, we have type constructors, and all we keep track of is what kind of type constructor is it. So is it a data constructor? Is it a new type? Is it a type family? Is it a class? That kind of thing. We have constructors, and this has information about like what is the constructor, how many fields does it have, how many arguments does it have, but not much information at all. And then for record fields, we need a bit more information, which I'll show you an example later where we use this information. But essentially, it's which constructors have this field. And this record field was in the type check. It's just in id. In id, you have some information about, like, I think I had it before. Right. Id, you had in the id details field, you had some information about record selectors, for instance, and it has some more information. Right. So then the key way that the renamer works is this thing called the global reader environment, so global reader env. And that's this environment that has all the information the renamer needs to be able to rename things. So ockenv, if you remember, is just a map that's keyed on occurrence names. So you look up both the textual name and its namespace, and you get all the global reader elements that it could refer to. And so a global reader element is its unique identifier, and then there's some more information about it. So it's unique identifier, then this is the information that the renamer has about it, which I explained in the previous slide. And then there's information about, this information is about how it came to be into scope. So the global reader environment is essentially like what's in scope, and then it gets shadowed by the local environment, as I'll explain later. But this is when you import things, you add to this environment of like all the identifiers you imported are now in scope in the module. And then when you define things locally, those get added every time you define something. And so depending on what it is, so if you've imported it, then it's going to say where you've imported from, and it's going to say it's not local. Otherwise, if you defined it locally, then it's going to be an empty list of imports, and it's going to be defined locally. But then there's some ways where it could be neither, or it could be both. So if you refer to something directly by name, for instance, if you do that in template Haskell, then it's something that's going to neither be local nor explicitly imported. You've directly specified like its unique identifier, and then we'll go and get it, say in the interface file. And then there's some weird situations with like HS boot files where you could end up with something that's both local and imported. But we don't really need to think about that.
When we refer to an environment, right, like an awk-env, this is really, you should think map, right? Like a finite map from an awk name to,
Right.
in this case, a list of, and just to make sure that was,
Right, yeah.
that's right.
Maybe
So
I didn't.
environment in general is a map.
Yeah.
It's kind of a bit of jargon that we might not have covered.
Yeah, so this is what it is, but I guess I did go a bit fast. But so this is like a map from strings to an int map. Sorry, no, it's the other way around. So it's an int map. Or it's it's basically two int maps actually. So it's like an int map of int maps, which is used to look up if you only got an occurrence name. So you got the textual name and you got the namespace. So this is kind of what we're going to be dealing with in the renamer. We're going to be constructing this globally read environment from things defined locally and from imports, and that's what we're going to be using to actually do the renaming. Okay. Any questions so far? I think I'm going to get into an actual example soon. Yeah.
For the map, like the int map of int maps, the first key that points to the other map, is that signifying the local scopes that are available?
No. So the first key is the textual name of the thing. So if it's like foo, just be foo. And then the second is what namespace is it in? Am I interested in a data constructor, in a type constructor? And it's set up like that because a lot of the times you might not know. You might, for instance, when you've got a promoted data constructor, you don't know if you're referring to like the type or the promoted data constructor. So you don't know if you're looking in the type constructor namespace or the data constructor namespace. So a lot of times you'll do a lookup and it'll tell you, well, here's what I have in all the namespaces. And then you can filter out, oh, I'm only interested in type constructors and data constructors. And then maybe it'll say, okay, there's only one thing it could refer to is the data constructor. I've got nothing else. Or it could say, okay, I've got both a data constructor and a type constructor, and then you're just going to have to disambiguate.
Okay, thanks.
For the way the scoping works, I think I'm going to get to it now. So this is the information we have when we're type checking and renaming. So both the type checker and the renamer, they run in this monad called TCM, and it has various other names. It's TCRN because both the type checking and renaming, and RNM. So they're all type synonyms, but like if you're in the middle of the renamer, usually you use this type synonym just to indicate to people that we're only going to be renaming things. We're not in a general type checking monad. So these are the definitions. And IOENV basically means IO, reader T over IO, which has access to an environment. And so env AB is something which has A and B as fields, and then it has some extra stuff that is available all the time in the compiler. So the first one is HSC env, and that's kind of like your global configuration options that you have per module. So it would be something like what language extensions have you enabled, what flags have you passed on the command line, things like what platform are you running on, are you 32-bit or 64-bit, all that kind of global environment that's accessible to the compiler in general. Yeah, there's information about all the modules you've loaded already and things like that. Then there's the type checker global environment. And this is kind of gets populated as you go along in the type checker. And it's kind of the main output of the type checker. This is like the full environment, like everything you've defined in the module ends up populating this global environment. Let's see. So like what types you've defined, what instances you've defined, this global read environment so that you can import it and have access to it. And then we have local things, which are parts of the environment that change as you kind of go, you recurse into an expression. You have an expression, then you get some environment, and then maybe it's like a top-level function definition, and then you go into like the where clause, and now the where clause is going to bring more identifiers into scope. And that's all brought into scope with this local read environment. I'm not sure if I have a definition. A local read environment, again, just a map you can look up from, but that one is kind of simpler because it only has like term variables, because you can't define like, I can't write a class in a where clause, or I can't write a data constructor in a where clause. I mean, some people would like that to change, I think, but currently we don't allow that, so they're separated. And then there's other pieces of information. So, for instance, one important one that I'm sure Simon is going to talk about in his talk is the type checker level, so which records, like if you've entered like a GLT pattern match, it'll record, okay, we entered a new type checker level, so that the new information you have inside that pattern match doesn't get propagated back outside. Right, any questions so far? I know it's a bit abstract so far. I'm going to go into an example. And in the second half, we're going to actually get our hands dirty.
Do you have access to the overlapping, whether or not the instances are overlapping?
Yeah, that's in the instance environment.
Okay,
Yeah.
you do.
I mean, you basically have the full information that the type checker has been able to produce about a module. But as I said, this is kind of generated as you're type checking the module. So if I'm renaming a module, well, I certainly haven't type checked it yet because renaming comes first. So then I won't yet have things for things that are locally defined. So this is kind of why we have this. Why we have this data type. This data type is like small amounts of information that we can figure out about things that are defined locally, because we might not have type checked the thing yet, so we might not know a lot of things about, like, is this a class, is this, or, well, we can figure that out from the Renamer. We can't, like, we figure out exactly what instances we have and stuff like that. So this is like a stripped down version of what information we have just for the Renamer. And this allows the Renamer to handle imported things and locally defined things in the same way. Because for imported things, usually you have a lot of information, right? You've already type checked the modules you're importing. So you're going to know exactly, you're going to have like tie things and everything, which is going to give you full information. But then for local things, you won't have that yet. So it's kind of useful to have like a basic data type that just has information that you can handle in the Renamer, which is this second data type. Right. So I'm going to give an example of renaming a record update. So generally, if you want to know, like, how does GHC rename a record update, and you just want to figure out in the code, well, you can just look, where does it rename an expression? And this is renaming an expression, the record update, and this is how it starts off. There's two cases it can handle. There's like a normal record update, or there's record update if you enable the overloaded record dot syntax. So I'm not going to be dealing with that one. So this is just normal record update. So we're in this, maybe I should have written the type signature here, but we're taking like a past expression, and we're supposed to return a renamed expression, which means that all the things inside it refer to these unique identifiers. And we're running in the Renamer monad. So what we're going to do here is we're going to start off by looking at the fields in this record update to find out what fields we're referring to. Because this is an update, if I don't have it written in the slides, but something like lowercase r braces, field 1 equals 3, field 2 equals false. So we don't know ahead of time which data constructor we're updating. We can't say like, oh, I'm updating the data type A with constructor muck A. So we have to figure out in the renamer which fields are, so if the first field we're updating is called field 1, which records have that field 1, and which update do we have? So there's some logic where we reject the record update if there's like a field appearing multiple times. I'm skipping over that. So we look up each of the fields, and so the thing that's happening here is we look up each field, and because we're in the renamer, so now I've got a type signature, so we're in the renamer monad, we've got access to the global read environment, and then we look up in the read environment what are the record fields that this could mean. And then we've got this GRE info attached to record fields, which is going to allow us to disambiguate. So here's an example of a record update. So we've got these two data types, and we've got a record update, and we want to figure out what data type am I updating here? And it used to be the case that we did most of this in a type checker, but it's much better to do this just syntactically. The idea being that if you want anything that's type directed, you use the overloaded mechanisms like overloaded record dot overloaded record update. So those are meant to handle record updates using like has-filled type classes. So then that's going to be happening in a type checker, and then it's going to figure out using normal type class solving, like what fields you mean. But generally speaking, we don't want to do that. We want to do it as early as possible in the renamer without having access to types, because you don't want to have like an imitation of the constraint solver inside the renamer, right? Because imagine one thing you could do is you could say like, to say that you mean the record update S, you could say R, you could add a signature, type signature around this, say R double colon S. And technically, that's accepted by GHC as a disambiguation mechanism currently, but we don't. But the general principle is that we're trying to do it purely in the renamer, so that we don't have to, like, because otherwise you have to end up doing ad hoc, like fake type class solving, basically, if you're not properly using type classes. Anyway, so what do we do in this example? So we've got these two fields, X and Y. But we're going to have renamed this already. It could be either imported or defined locally. So we're going to know what things we have in the read environment. So we look them up. So X could refer to quite a few things. Could refer to this X, this X, this X. So you get information like that. So X could belong to any of these data constructors. Y could belong to any of these data constructors. But you want a data constructor that has all the fields, because otherwise the update wouldn't be valid. So you take an intersection, and well, you see T1 doesn't appear in the second one because T1 doesn't have Y, and T2 doesn't appear in the first one because make T2 doesn't have X. So you end up with these data constructors, and then at the end, what you really care about is the parent data type. So you just, given the data constructor, you can look up what the parent type constructor is, and so you get it as a unique parent. And so then you're going to say in the renamer, right, the parent for this record update is S, and then when it comes to actually type checking the record update, is going to know, okay, we have this is what data type it's updating. Anyone have any questions about this example?
Maybe it's slightly unrelated for the purpose here, but there is an extension that allows ambiguous record fields. Is that then handled at a later point in the compiler, or is that?
That's handled in the renamer.
Okay.
So, well, Right. So what do you mean by ambiguous? Do you mean when you need to disambiguate using a type? Or do you mean duplicate record
Good
fields?
questions. Yeah, I meant duplicate record fields.
Right. Yeah. So I mean, this is the whole. This is. I should have said sorry that this is we're relying on having duplicate record fields because if we don't have duplicate record fields, then we can't declare the same field give the same name to different data types.
Okay.
So
I'm all
so
clear.
this is like how to do disambiguation when we've got duplicate record fields. Because otherwise, if you don't have duplicate record fields, then X is only ever allowed to refer to one thing, and then there's nothing to do.
I think my question was answered. Basically, you're saying that it's an error now. If it finds that it's ambiguous at this point, it's going to be an error. It doesn't defer to some type checking stage.
So if it was ambiguous, so there were two data types. Currently, there's still some like very ad hoc rules for saying, as I said, you could just like give a type signature to R. So say R : S, and there's like some special logic in the type checker that will recognize that and say like, oh, that the user must mean S. But that's like very like hacky logic, because if you were to write R : a type family and the type family reduces to S, it wouldn't work. Or if you wrote something that wasn't like syntactically immediately just the type constructor, then it wouldn't know, because the way we figure out really this should be part of like constraint solving. The way that works is by using has field and set field and things like that. So if you're using has field and set field, then it gets fully disambiguated using.
Isn't it deprecated now to use a type signature?
Right, it is, but there's no replacement for disambiguating yet.
Right.
So I have some tickets later on in my second part of the talk that suggest possible ways we could do that.
Great, thank you.
To quickly go through how we process the information throughout the renamer. So we use this trees that grow. We've got this type family idp, which is an identifier for that pass. So it could be in the pass, in the renamer, in the type checker. So what you're supposed to understand here is that the parser produces reader names, and the inputs to the renamer which get names, and then the type checker elaborates and gives full information to things, and it gives it id. And then there's this lidp thing, which just tells you where things are defined to keep track of source locations for like printing and error messages. So I kind of explained earlier what we're doing in the parser. We're creating these occurrence names, ocname, just using make qual and make unqual, which are create like qualified and unqualified names. So this is like code from the parser, which passes a type constructor. I'll skip that. And then, right, let's see how renaming and type checking works. So this is the global flow of renaming and type checking a module. So you start by renaming the imports, and that's going to bring in scope everything that you need. Then the renamer is going to rename the things that are declared locally in the module. Then you type check them. And then once you've type checked everything, you do renaming for the export list. And as I said, the key thing you're supposed to, so in this way, the rename and the type check are kind of interwoven. And the reason for that is things to do with like splicing in template Haskell and having to then type check that again. So there's kind of an interplay between the rename and the type checker, but I won't go too much into that. And so for import is really easy. Imports is basically you just figure out what you're importing, and the module you're importing is going to have the global read environment that you need in the renamer. So if you've got like just import M, then it's just going to take in the whole read environment that module defines, and otherwise you filter out things. So if you'd say import M, A, X, and B, then you filter those out. And so that gives you the global read environment at the start of processing the module. It has all the things you've imported. And then there's handling the things you've defined locally. So this works in there's like two stages. The first thing you need to do is give unique names to everything to uniquely specify, like, okay, this is the class and it's unique is 17, this is like, etc. So you generate new names for everything. So it happens in this order. We've got like type declarations, classes, things like that. Then pattern synonyms, and then the left-hand sides of value level declarations. Because we all could be recursive, so you need to be able to know what everything refers to in the right-hand side types. You need to be able to say, oh, it refers to foo defined at the end of the module, for instance. And then what we do, once we've got this information, so that is going to have given the names of everything, uniques, say like, this is a unique for this, is unique for that. And then we can actually proceed to disambiguate whenever we have occurrence of things, like in the right-hand side of a function definition or in like a definition of a class or an instance, then you have to say like, you process the AST and say what the unique were for everything. So kind of that's the flow of that happens in the renamer. Okay, and in the next part, I'm going to just go over like an actual worked example where we're going to look at some code and get you to like start using HLS and see what we can figure out about GHC. Right, so for this second half, we're going to follow along and see how I fixed the bug, and we'll figure out like how to figure out what parts of the compiler needed changing and things like that. So let me start you off by explaining what I was actually trying to solve. So this is a problem we have currently. So we're matching on the pattern U in the do statement there. But for some reason, the compiler doesn't, and the idea is that this pattern shouldn't never fail. This is obviously a bit of a contrived example here, but you can imagine another kind of example where you're matching on something and you know the pattern match is going to have to succeed. So, pattern matching on like a vector or something like that, or like a pair of elements or something like that, where the inner patterns are variables, so it shouldn't fail. But here, for some reason, GHC thinks that this pattern match can fail. And so it says, well, you can't find any instance for monad fail identity. So this is, like, we can take this as what the user has reported on the bug tracker. They've reported something like that. So I've got a few examples, like this basically same issue has been reported a lot of times where we have a do block and a pattern match, and in certain circumstances, GHC isn't smart enough to realize that the pattern can't fail. So it pessimistically assumes, oh, maybe the pattern match can fail, and then starts trying to desugar the pattern match in the way that uses the fail operation. But let's suppose we don't know anything about this. We don't even know why is monad fail happening.
Sorry, I have a question from online from Gago Erdi. Is this problem worth fixing when the plan is to overhaul do syntax desugaring completely anyway?
Yes, because you're still going to have to do that in the renamer. So our task is to figure out how we can improve. So, well, we're going to figure out that this is an issue in the renamer. And so no matter how we overhaul it, we're going to have to fix it, like improve the situation in the renamer. And the fundamental problem, I think, can't really be addressed. What is kind of going on is that in the renamer, we're handling this do notation, and we need to figure out whether we need to emit a monad fail constraint or not. But we need to do that in the renamer before we've type checked and before we have the types available. And in general, we might need to do that. So there's other examples here than this one where we're not matching on a pattern. So in this case, we're matching on a pattern synonym, but there's other cases where you could be matching on a GADT, and you would need type information to be able to decide whether the pattern match is complete or not. And so in that, we can't really do in the renamer. So what we're going to do is just try to solve this one problem, which is to do with pattern synonyms. So let's figure out what the issue is. So, I mean, in this case, we were emitting a monad fail constraint. So let's try and search where monad fail comes up. So if you just do the most naive thing, we can just search monad fail in the compiler, maybe. Um, Right, so this is like the most naive thing you could do. You just search for monad fail in the compiler and try to see like where is this happening. And obviously we're going to think, well, it's going to be somewhere in the renamer. And so we land here, for instance. Let's see. Right, so for instance here, we're renaming a bind statement, and we call this monad fail op. So which seems like it's probably going to be relevant. Let's see, and then if we go to the function, we land here. Can you increase the font size? Yeah. Right. So, right, here, for example, we're in this function monad fail op. And what do? Well, the first thing we do is we check, is this pattern irrefutable, which means the pattern can't fail. So if I go to it and then go to the definition. Right, so we land in this function, is irrefutable HSPat. And then you see we're doing a case on the various kinds of patterns we have. So a variable pattern, a wildcard pattern, I mean, that can't ever fail. A variable pattern can't ever fail, etc. What we're interested in is, in this case, conpat. And here we see what's happening. We're deciding, well, if we're in the parser or the renamer stage, so this function is given in a pattern, but it might not have been renamed yet, or it might not have been type checked yet. So we're getting, if it's at the parser stage or renamer stage, we're just saying, we don't know. So we just assume it can fail, which is obviously kind of the problem here. And you can see even in the type check stage, we still conservatively say, for a pattern synonym, it can always fail. So one idea we might have is, let's change this function so that it can be more accurate in this situation. So if I go back to the slides. So, right, here's where I found this was happening in the renamer. There were two places. There was that one we found earlier, and then there was another, there was just that one. And then there was also some in the type checker. These two cases did do a kind of similar thing of type checking a bind statement. You would, again, do something to find if the pattern can fail or not, and depending on whether it can fail or not, you would introduce a fail operation. And kind of the key thing here, and as Gerger points out, the thing that's probably likely to change is how this basically is the way we're going to instantiate and say, okay, we need a fail operation, and that's the fail operation for monad. So it's going to be like fail for all m, string to ma. And then the type checker is going to instantiate this fail operation, in this case to the identity monad. And that's why we got no instance for that, because that function instantiated that function which would emit a constraint and end up saying, and requiring this that we can't fulfill. Right. So, right, that's what I said. So we're in here, and we decided we're going to improve that. So we could figure out how to pass information here. So the problem in the GHC RN stage is, what information do we have attached to data? Like, even if we're handling the other case, not just pattern synonyms, but for the data constructor case, we can still do better than this always false, right? In some cases, matching on, unit, that's never going to fail. So we can at least do better there. So we can figure out what information to pass. So maybe I'll get up the data type. Right, so This is the pattern data type that we use at the various passes. And what we were interested in, let's see where we find it, right. So this is the constructor pattern. This, as the field name says, handles the arguments. So we're not really interested in changing that. And then here we've got these two things here. So this is the extension field. So this is just data that can change at each pass. And then here we've got this, which is also changes at each pass. Let's see, okay. Right, so for instance, this is what we have, how we represent a constructor for the patterns here. At the rename stage, we just say it's a name. So for instance, this is kind of annoying because it means we don't know if it's a data constructor or pattern synonym. Obviously, if you have the name, what you can always do is like look it up. But it would be better to store the information you're going to need in order to like handle the pattern. So in this is irrefutable HSPAT function, right, you can see we're doing a bit of a different logic, even in type checker case, whether we've got a type constructor or pattern synonym. And for if it's a data constructor, well, what do we need to know for it to never be able to fail? It has to be the only data constructor that data type has, right? Because if you've got like a sum type and you've got two data constructors, A and B, and then, well, matching on A could possibly fail because maybe you've got a B. But if there's only one data constructor, you know then matching on it can never fail. So that's the condition that's happening in here. So it would be good to keep track. If we want to get this correct before we've type checked, we'd like to know, well, if the thing is a pattern synonym or data constructor, and if it's a data constructor or pattern synonym, and if it's a data constructor, we'd like to know, is it the only data constructor of that data type, or are there multiple? So then we can figure out, well, let's store it, we can store it. So this, conlike P, I didn't quite explain, but that in the type checker it says, but conlike is something that can be either data constructor or pattern synonym. And I can go to the definition. Right, so this is when you have the full information, when you're on the type checker and you've type checked the pattern synonyms in your module, the data constructors, and now you're just like renaming the rest of the code. And you know it's either data constructor or pattern synonym, and this has like everything you would possibly want to know about the thing. We don't want the boot file. Right, so what kind of data constructor it is, where's there's datacon, tycon, no, reptycon. I think, yeah, this is where the type constructor is stored. Right, so you can access a type constructor, and then through the type constructor you can access all the other data constructors of that parent type. So you basically, this is when you have the full information in type checker, but we're not going to have that. So we could still distinguish between datacon and pattern synonym, but we need a bit more information. So as I said, for the data constructor, we need to know if it's the unique one. And for pattern synonyms, there's a few things you could say, but I think what the approach we're going to take is we're going to look at user-provided complete pragmas to decide whether it is complete or not. So for that information, but that's kind of environment, right? The pattern synonyms, the complete match declarations are defined somewhere else in the like it could be imported from other modules, etc. And they could be like loads of various sets that are defined using data constructors and patterns that are defined in different modules. So you can't attach it to a single thing. So I've decided what we should probably do here is this function is irrefutable HSPAT. We're going to just pass it the environment of all the complete pragmas that are relevant. And one of the reasons I've decided to do that is I think if we've got all patterns, then we might want something like this to also work. So we've got two, say, pattern synonyms, P and Q, and we've got a complete pragma that says if you match on, like, they form a complete set. And then you can imagine if you have an OR pattern, which I'm not sure if that's quite is that the latex syntax? And so you can see in this case, well, that shouldn't fail because we've said P and Q are complete sets. So if we check mean, this is a bit of a useless thing to do because really, what might be more interesting is if they both bind variables, but we won't have that straight away at least. But you should probably accept that, right? Because you said, well, P and Q are a complete set, so matching on it should never fail. We shouldn't, when we try to type check this, we shouldn't require a monad fail constraint for that do block. So in total, the information we're going to pass is for a data constructor, whether it's the only data. First we need to pass whether it's a data constructor or pattern synonym. In the case that it's a data constructor, we're going to pass whether it's the only data constructor of its parent type. And if it's a pattern synonym, we're going to separately pass the environment of complete matches. So this is kind of what I'm going to be storing in this xconpat thing is some data type like this. So with the understanding that for the pattern synonym case, we're going to have to look at the complete matches which are going to arrive separately.
What happens if the complete pragma and the pattern for which it is defined are in the same recursive group? If you define a pattern which in its definition uses an irrefutable pattern match like this?
I'm not sure that's allowed. There's like restrictions about recursion in terms of renaming and type checking of pattern synonyms. Like you can't have pattern synonyms, you can't define two pattern synonyms which are mutually recursive, for instance.
Okay.
I think that might be able to be improved. I don't quite know. So let's say we want to pass these complete patterns to this irrefutable HS pad. Well, the first thing we better do is like figure out how these are represented in the compiler. We can just like do the same thing I did earlier and just do a kind of search where these defined and used. And so here are the two main data types that define where the compiler handles complete matches, complete pragmas. So there's a sig data type for signature, which is a thing that handles giving type signatures to top-level functions, for instance. And that's kind of part of the AST of the module. So you're going to pass it, and you're going to pass the signatures for things, and that includes the complete pragmas. And then the separate thing is where this information gets recorded. So, for instance, the pattern match checker, which runs after the type checker, is going to have to know like what the user has declared, what are the complete pragmas. So where does it get that information from? And it gets that information from the type checker global environment. So we've got this field there, TCG complete matches, which just takes a list. Yes, I should have said complete matches equals list of complete match. And so the complete match just says, what are the constructors, which could be either data constructors or pattern synonyms? And then what's the result type constructor? Because you're allowed syntax like A, B is complete only at type constructor T. But I'm going to ignore that for now because we can't really deal with that in the renamer. So we want to pass kind of this, we want to like pass information like this, like some list of complete matches to this irrefutable HSPAT function. So one way to figure that out is to use HLS and just see where this is called. So let's see. Is irrefutable HSPAT? All right. Show call hierarchy. Hopefully this works. Right. And now we see that we've got these examples. So we see we've got two situations in the renamer. So it's in the GHC.rename, and we've got two in the type checker, thc.tc.gen, and type class. So let's see this one. Right, so here we happen to be handling like applicative do, and we need to figure out whether we need a monad fail constraint. And then let's see, what else did we have? That's it. I've lost it. Sorry. Right. Yeah, it doesn't. Yeah, it doesn't really matter. So that's what we're looking at just there, and then here's another one in the renamer. Oops. Here, well, this is where we were looking at earlier, basically, right? So the information needs to fail to flow to this monad fail function when we're renaming statements. Right. So that's pretty much what I showed. And well, yeah, we're going to need this information in the renamer. So we can't quite use this type here, because this is information we have once we've type checked things. So as I said, for instance, conlike has the full information about a constructor, so it knows everything. So we only have that once we've type checked the module, but we need this information in the renamer. So we can't quite reuse this field, which is unfortunate. But one thing we can do is, it's a bit ad hoc, but it's because the type check environment is the same for the renamer and the type checker. So we're just going to store it here. I mean, could probably store it somewhere else. We just store a stripped down version with the information we have in the renamer. So the thing here is that the constructors, we could technically store whether each individual constructor in the complete set is a data constructor or pattern synonym. We don't really need that, so we're not going to store that. So we're just going to store the names of them. And the other thing you might notice is that I've also dropped this, the other part we had. Right, the result icon. I'm not going to be storing that at all, because a complete match is only going to be, if you have a result icon in your complete pattern match, complete pragma, then it says this complete pragma only applies to this particular type. But in the renamer, we're not going to know what the types are. So we're just going to pessimistically assume, like, okay, if it's got a type signature like that, we're just going to ignore it. So I'm just going to be dropping those. Alternatively, we could still store them and just ignore them when we look them up. It doesn't really matter. So now we have to figure out, we've got this information that we're going to want to pass in the type checker. I'm going to figure out how we actually pass it. So we're going to look at where monad fail op is called. So you can use the call hierarchy thing again. Here's one caller hierarchy I found that essentially what's happening is, well, the one at the bottom is like we're just renaming the module. Okay, so at the end we get there, so that's good. And then we kind of need to find, well, where are we renaming things where we're going to get these signatures as input. We get those, and then on the back of that we accumulate the complete pragmas, and then we can pass it to other things that need it. So if you want to find that out, you could look at the call hierarchy and kind of just like browse around. You need to find a path that goes all the way from this to the rename source decals, because you could easily branch out in irrelevant places, like rn_exp is called by rn_located_exp, which calls itself, or etc. So you want to kind of go all the way down to here and then find where in the middle is relevant that we could be passing this information. And so if you search, you find this, which is quite promising, because if you remember, these complete matches were stored in this sig data type, which just handles type signatures and things like that. So we're in the renamer, and what are we doing? We're renaming the signatures, and then we're renaming the top-level value bindings of the module. So this seems like a good place where, and inside here is where we're going to end up renaming like the do block. So what we can do is, well, we're renaming the signatures and well, we can accumulate what the the sets of complete pattern matches are, and then pass those on. So, so you can do something like what I've written here at the bottom. So I'm missing that this should also like return or, all right, yeah. So I have like a function here, add complete sigs rn, which is what it's going to do is going to take all these signatures that we've renamed. So now they refer to the names of everything, the unique names of everything. And we add them. So I've got this function, which is the obvious thing. It like goes through the signatures, finds which ones are complete matches, and adds them to this environment that we've defined to this field here. And it just passes it on. It updates the environment so that this function, which renames the bindings, sees all these signatures. But this is not quite right either, because this just handles signatures that are defined in the current module. But the sets of complete matches might have come from somewhere else. So they might have come from an imported module. How do we get all these complete matches that come from other modules? And you think, well, the compiler's already going to have to do that somewhere, right? When the pattern match checker runs, it's going to have access to all the complete set of pattern matches from imported modules as well as locally defined ones. So we can just kind of look up where we kind of use this field and like add on to it with the other pieces of information. And so the functions I found just by looking up this TCG complete matches function in the compiler and seeing where it's used, I find these two functions: make dsugar envs from tc global env, and init dsugar with modguts. So it's kind of where you'd expect them to be is you finish type checking and then you're going to run the desugarer, which is going to do pattern match checking. Well, at that point, you're going to have to go from the information in the type check environment to the information that the desugarer needs to desugar and do pattern match checking. So it does something like this. It gets these type check environments and just accumulates everything. So you can just do the same thing. Any questions about this so far? Right. And so now that we've got the full information, we can update this function. So what we're doing, remember, is we were storing some extra information in this extension field to say whether it's a data constructor or type or pattern synonym, and if it's a data constructor, whether it's the unique data constructor of its parent. So we can refactor this function. We can say the constructor pattern is irrefutable if the constructor is okay, and then all the patterns are irrefutable. And for the constructor, now in the GHC Rn case, now we look up. So for the data constructor case, we say, well, is it the only data constructor of its parent? And then that tells us whether it's irrefutable. And then for the pattern synonym case, we can look up in this complete environment to see if any of these is like a complete set that contains a single element, which is our pattern. Right. So, any questions about that so far? Yes. Question from Ryan.
A couple of slides ago, if I understood correctly, you sort of have to load all of the pattern synonyms from interface files during the renamer. Is that right?
Yeah.
And later you also have to do this when doing pattern match coverage checking, which is a separate thing.
Yeah.
Is there duplicated work there, or does the information from the renamer somehow flow into that?
The way that usually works is if stuff is already loaded, then it's just going to find it, right? Because it's just doing name lookup, and if you already have it in the environment, it's just going to directly return it.
Okay, that makes sense.
But you could imagine another situation where you try to do something a bit more like trees that grow, and you store like a renamer level complete pattern match set. And then once you finish type checking, you just update that. I think which is probably a better thing to do actually. Because I'm just like adding a new field to the global environment is probably not the best approach, but you still have to like parameterize the field so that it handles both the renamed and type check stages. Now that we've got something working, well, we think we've got something working. We've kind of like fixed up this function to pass all the information it needs. And then this function was the one that was determining whether the pattern match could fail in the do block and deciding then whether to emit monad fail constraints. So we try a program like we try the program in from the beginning of the slides where we pattern matched on you in a do block, and you end up getting this error. Like, what the hell is this? So you can just like search where in the compiler are we emitting this error, just to try to get what is it? Right, so we land here. So in GHC HS to core, which is the desugarer, and we're in this situation, and somehow we've determined that we're in this MR fallible case, whatever that means, and then we try to look up a monad fail operation, and we see that we don't have one. So it's like, why is this happening? Because you think we've now made it so that we consider that the pattern match can't fail. So why are we still determining that we're in MR? Why do we land in this MR fallible case as opposed to what you'd think would happen is we end up in this MR infallible case? So what's happening is that in that same module, I think the function that creates that desugars like a pattern match on a pattern synonym. It does this, which means it always returns this MR fallible. So it says, like, pessimistically, it always assumes the pattern match can fail. And, well, we might wonder, like, well, now we've said it shouldn't fail. So there's two things. One thing you could do is you could update this code to say, like, if we know that the pattern match can't fail, just change this to return MR infallible in that case. You can do that, but you might not want to because of a situation like this. So the user might have provided a complete pragma that is a bit of a lie. So for instance, in this case, the user has said, we've got the pattern bogus, which is equal to 3, and they said it can't fail. So now if you imagine we're in a do block, and we pattern match on that and on something that isn't 3. Well, what should happen here? I think one thing you could say is, well, maybe we should emit a monad fail op in this case already. And so in that case, you would need to pass more information than just complete pragmas. So for instance, I mean, in this case, what we could do, we could look at the right-hand side of this pattern, and we see, like, well, is the literal pattern 3 an infallible pattern at type int? Well, obviously not, because we can match on an integer and it could be something that's not 3. So we could decide to, like, look more into the pattern and pass that and decide on the basis of that, which would essentially mean in this case ignoring the complete annotation. But the other thing you could do is you could kind of treat it differently and say, like, okay, we're going to accept this program at the bottom, as in we're going to compile it. We're not going to throw a compiler error. We're not going to say, like, no instance for monad fail identity. But when we actually run it, we instead of using the fail operator from the monad, we're going to just fail as in the same way as a normal pattern match fails. So this is what I've done here. I've updated this function we saw to say, well, in this case, it might be that we generally don't have a fail operation, but we still want to fail. And so the way we can do that is through these like error IDs that are baked into the compiler. And if you didn't know about this, you just like search into the compiler, like how are pattern match exceptions reported when a pattern match fails and there's like no default case. So I've just copied this for now. It can be improved. And this required a few changes. This error, you need to know, well, you're throwing an error, but you need to know the type at which you're throwing the error. So you're going to have to like change around a few functions here to just pass the type explicitly so that you have access to it here. Or I mean, there's several other things you could do. You could just change this monad fail op, because currently it's a maybe of something. You could just like automatically just fill it in with this, for instance. It depends on what people expect to happen with like complete pragmas. Like, because here already we're in a situation where we've got like a complete annotation on something that can fail. So it's like already not clear what people expect to happen when it actually does fail.
So I guess the point here is that this is sort of implementation-defined behavior, despite the fact that we're not, which is fine. But yeah, it's a useful lesson, I think, is, if you find that the behavior compiler does something, it doesn't necessarily mean it does the right thing. In this case, we find that we could change it, and it would be well justified to do so.
Yeah.
Okay.
Right. And so in this, if you compile this program now, with the change, you get something like this, and you just get a generic error, which is not necessarily very helpful, but you could improve that. Sorry, here, if we actually look at where these are defined. All right, and then we can look at part error name. Yeah. Right, so this is just where we end up with that, and we just get some generic part error, which I think is what we're seeing? Right, I think, yeah, that's what's responsible for the error message there, but we could update and use a specific id that would say, like, we could like give a specific error message for this situation, say like, a pattern match failed on like on something that has a complete pragma on it, but it failed anyway. But I mean, as I said, the other thing we could do, we could just decide to ignore this complete pragma, or just like say like, well, this pattern match really can fail, and then just refuse to accept this program, and continue with the old behavior of requiring a monad fail operation. So to do that, what you'd have to, I mean, I guess you can look at what information we have about a pattern synonym. Again, what we could do here, I think we don't store whether the right-hand side of the pattern could fail, and that might be a good piece of information to have, because here we've decided to do it on the basis of complete pragmas. The justifications for that, I think one of the justifications was, I mean, this is the error that many users are reporting. That users are reporting, they define a complete pragma, which says like, well, I've matched on all these, so it shouldn't fail. and it's actually failing. So when we could just trust the user and say like, well, they've said a pattern match is complete, so we're going to accept this, and then crash at runtime if they pattern match actually fails. Or the other thing you could do is, well, and the other reason I thought it was interesting to look at complete pragmas is because you might want to use them when there's multiple. So that was the OR patterns example. In that case, like there's just no way the GHC is going to be able to figure out like that a combination of like this pattern synonym here, this data constructor here, etc. is complete, and then, or maybe there's a way of doing that, of like improving how we figure out without requiring the users to create complete pragmas. But as I said, the other thing we could do for this particular case, for a single data constructor, we could just not ignore the complete pragmas completely and just decide on the basis of the right-hand side and say like, well, this is a pattern that can fail, so we're always going to consider it that it can fail, even if they write a complete pragma. All right.
But then there's one other thing, and that is you've changed the semantics of user program.
Yeah,
so
yeah. Then you
document
realize
that. Where would we write that? That's.
I mean, depends on what you want to do, but I think how much you. Yeah, I think once you realize that you're going to have to be like changing things in unpredictable ways, and that ways like that might start rejecting programs. You'd probably have to, I mean, usually it'd be flagged up during review that they might need a GHC proposal, or at the very least what you might need to do is say like, okay, well, we accept this as implementation defined, but let's at least check that we're not breaking anyone's programs. So the way that's usually set up is, well, I won't go on them now, but if you submit a merge request, you can attach a little label to the merge request that says user facing, that says the program might like change which user programs compile or how they run or things like that. And then what that is going to do in CI is it's going to make sure it runs head.hackage, which is a collection of packages from Hackage which have patches to make sure that they build on the latest version of GHC. And it'll see, have we broken any user programs? So one thing you a typical situation might be, you say like, maybe I can just squeeze through, and you just see that I'm probably not breaking anyone's packages. And then if people reviewing the patch think it's okay, and that you head.hackage just pass it, and it's probably going to be okay. But in another situation where you might be like breaking packages, or in this case, you're kind of like potentially silently changing behavior in an unexpected way. Maybe the person was relying on monad fail for erroring in a certain way, because then they would catch the exception, and now the exception is thrown in a different way, and it messes up their programs. You might have to write up a GHC proposal to suggest we change it, and then that's going to get through review and let someone come to a conclusion.
If I might just one more place is release notes. Yeah, that's a great place.
Oh yeah, well once you've decided that you're making the change, yeah. There's release notes, and the other place you should probably update also the migration guide, if there's any like changes that need to be made for people to adapt their programs. Well, it depends what you want to do, because here, originally, without this change, what happens here is that failing pattern matches in the left-hand side in a do block use the fail operation from the monad. So that's the way the original program was rejected. It said there's no fail operation in the identity monad. So you could just, as I said, basically ignore the fact there's a complete pragma here, because the pattern match can fail. And so you would just go back to the old behavior. But were you suggesting to do something like a third thing of like saying reject with a different error, saying like you're not allowed a failing pattern match, that like you've introduced a potentially failing pattern match in a do block, and I don't know whether to use monad fail or to use a normal error, so I'm giving you an error.
Yeah, a more specific error for this.
Oh yeah. Well, for the getting a more specific error, that's what I was explaining.
Yeah.
This pad error ID thing here, where we're using the generic like pattern match failure error reporting mechanism, and you could like create a new ID which would report a better error message than just this generic one. That's one way you could do it. Okay.
Maybe I missed something, but I thought that the desugarer applied after the type checker.
Yeah.
So, but you're working on the renamer.
Yeah.
And so why does the renamer need to desugar do blocks?
Yeah, I mean, that comes back to the original observation by Gergo online, who said, like, probably a like general way to handle this would be to try to expand do blocks in like there's this general. I mean, in fact, right. If I go here, so there's this project to change how we handle a lot of these things. And from like stopping all the to exactly circumvent this problem of the renamer shouldn't have to be doing these things because it doesn't have enough information. So there's this.
Is it because you have to be able to rename monad fail?
Well, but you need type information to decide whether the pattern match can fail.
Right, right. No, but I'm just wondering, like, why is it that you're facing this problem? Why does
but yeah, right. So this ticket is basically saying we should handle this in a different way, that we don't end up in this situation where so I think there's where's my the list is there, right. So for instance, there's this MI in progress 10140 which decides to change how we desugar, how we handle do notation, so that we don't have to make these decisions in the renamer anymore. But that's like that is probably the robust way of handling this. That would mean that we don't have to answer these questions in the renamer where we don't have full information. We should be able to do it when we have all the information we need. So,
okay,
does that answer your question?
Yes.
Be like, why was it done in the renamer at all? Like, what was the original motivation for placing this there? Maybe that's beyond the scope of this talk, but that would be maybe a similar idea.
So the distinction about what's done in the renamer and what's done in the type checker sort of seemed obvious to me to begin with, and then turned out to be less obvious in practice. But the basic idea originally was, well, look, in the renamer we're going to do just scope resolution, including things like if it is going to turn out in the future that we are going to need fail to desugar this thing, then we better attach fail to the syntax tree at the renamer stage, because we attach all the names of everything we need to the syntax tree at that stage.
Right, exactly. I mean, it's kind of for this dependency analysis thing that I was talking about, where you have to see what you're referring to. If you're, for instance, using the binary syntax, you might be if the do block can fail, then it's going to need a fail operation, and the fail operation might be defined in that same module. So you better make sure that you type check the fail operation before you type check the do block. So then you have to, in that do block, record that you're going to depend on the fail operation.
But nevertheless, this plan of always leaving the syntax tree undisturbed, type checking the original syntax tree, which is my original plan and seemed very attractive, because then you get error messages in from the original syntax tree. I have questioned that. I think maybe I'll take a few slides tomorrow to explain what we're now moving towards, so that you can sort of see the plan of record for that.
Yeah, I just like to point out that's a very cursed scenario, because since the type checking depends on the use of monad fail, then the type checking depends on how to desugar, yet how the desugar depends on how to type check. So we have this causality loop that cannot be done nicely and totally correctly without heuristics in any of these methods. So stay away from that problem, or this sort of problem. Don't get yourself in that situation where A depends on B and B depends on A.
I'd just like to say that as a user, if I say that this is a complete pattern and it's an int and it's 3, I'd like the compiler to tell me, no, it isn't. Right. I know that's difficult in general.
No, but maybe you do want that, right? Because maybe you've got maybe you're only supposed to be able to construct the values of a data type in a very specific way, and you have some abstraction layer with the pattern synonyms. So the only way you can create a value is with a smart constructor, and every time you use a smart constructor, then you guarantee that the pattern will pass. So for instance, if you the smart constructor could desugar to some kind of normal form, and then the pattern would just assume the thing is in normal form. So you can imagine that as like for library design reasons, you might want to allow users to lie about it. But again, this is like a design question. So probably would have to go through GHC proposal to decide if we should make a change and start. Realistically, we're not going to want to start rejecting loads of user programs if they've got like complete pragmas that can fail. And then, yeah, if you've got more than just one pattern, how do you decide whether it can fail or not? I was just talking about what things people might be able to work on, improvements to do with the renamer. And so this is one of the big ones, which is, well, changing how we desugar these things in the first place to avoid all these problems of like needing to know things in the renamer that we actually only really need to know after type checking. And as I explained, they're kind of really related to the rebindable syntax because they're related to the fact, like for this fail operation, we needed to know the fail operation in the renamer to be able to declare dependency. So I'm still not 100% sure on how this will be tackled in this particular case. But there's a lot of things in that basically the rename is currently doing that can be changed to use another method, which is this thing called HS expansion, where we kind of expand out an expression to something while still retaining the original. So it's kind of like macros in a way. And then when we're reporting an error, we always report in terms of the initial user-written thing, because otherwise we're degrading error messages. And so if you're interested in some of this, for instance, there's some notes in the compiler. I think probably the most, well, there's these two. This is readable. Rebindable syntax and HS expansion, and handling overloaded and rebindable constructs. And there's a lot of quite easy things to be done. So do notation is probably one of the hardest. I mean, just below that there's arrow notation, which is probably going to be even worse. But other than that, there's a lot of things that can be handled quite easily. So for instance, the way we handle literal patterns when you've got rebindable syntax enabled, how we handle string patterns when you've got overloaded strings enabled, things like that. They're handled in a very ad hoc way in the renamer currently, and we would like to make them be handled in a more uniform way. So that's some suggestions of things that can be worked on. And otherwise, there's a few tickets about how we do dependency analysis when there's view patterns involved, because that can be a bit complicated. Because if you remember in the previous talk, I explained in what order we rename things, and we'd start off renaming left-hand sides of bindings, and then afterwards do right-hand sides. But now the left-hand sides might have patterns in them, and some of those patterns might be view patterns. And so now you need to make sure to account for that properly in the dependency analysis the renamer does to decide in which order to rename the module. And there's currently bugs with that might be interesting to look at. And then I've listed here a few error messages that can be improved. And I think, right, and then there was a question, let's see, this is one of my tickets. There was a question about how we disambiguate record updates, and about currently, if you really have to disambiguate, you have to use a type signature. Yet if you do that, the compiler is going to complain and say like, this will be removed in a future release. And it has done so for like 4 releases now or something. But the reason is because there's not really a good substitute for it. One substitute is like using type class disambiguation. But if you can't use type class disambiguation because that has its own limitations, like handling of JDTs or handling of unboxed types or things like that, if you want to disambiguate syntactically, one thing you could do is say something like this. Maybe I should make this a bit bigger. Right. You could say, I'm doing a record update on the record R. Here I put the at pattern on the left, but you could put it on the right. Oh, no, you can't put it on the right. No, you have to put it here. Right. So you say R, and by the way, I'm telling you, R has type, like R is a make A. So then in this record, you could pass on this information in the rename and say like, okay, well, we're definitely doing a record update at make A and not B. And that would be a way of disambiguating. And the thing that, why this is, I think, decent is that, I think the other ticket mentions this, whichever the other ticket is, right, is that if you've got data families like this, it's quite complicated. For reasons I won't really go into, you don't even have a name for a data family instance in the renamer, because the way we generate a name is like, we generate like fam A, like as just like a single string kind of thing, and give that a unique. So we only do that in a type checker. So there's really no way, apart from using constructors, to disambiguate if you're not using types. So and this is kind of like the most annoying case for like is there a record update here? Right. Like in this example, he's done the same thing that I was doing earlier, which is say B, he's written everything. There's a type, here's a type, here's the qualified. So you can't qualify the field because you can't selectively import just one instance because it's a data family. So you're going to import both. So what you have to do is you have to do something in terms of the constructor. And then the way you do that is by saying here, well, my pattern is using this type. I'm interested in this field and not that field. And so we're kind of waiting for someone to come up. I mean, this is an idea. If you have another idea for disambiguation in the renamer of record updates, then we can finally get rid of those kind of hacks I was talking about with type, like accepting like a specific type signature for record update, but you wouldn't accept it if you had a type family in it or something. So that's about it for me. But if you are interested in taking a look at any of these tickets, just if you want like an explanation of what the ticket is about or want to get started with it, just come and talk to me. All right, thank you.